Alright, hi everybody. Welcome to Tuesday. Hopefully you had a good weekend and then that nice little bonus Monday. So what we're going to do today is we're going to kind of review some simple harmonic motion ideas so that by the end we can be able to construct an explanation regarding how they keep Big Ben running on time. So I was watching some videos about clocks, and this is just like the coolest thing to me, this idea that this whole country used to be run by this one clock, and everybody was on the same time, and that was kind of like what everything was based on. And the way that they would fix it if this thing got out of time is so simple but so smart, and I really like it. So it's kind of a cool thing, something that we'll be kind of looking at when we're building up our ideas of simple harmonic motion. So hopefully this is going to be a quick little review, and then I'll give you some simple harmonic motion practice questions and momentum practice questions, along with a free response that kind of ties them both together. Then just kind of coming soon, soon we have the AP test. So the AP test is going to be on May 14th for you guys. Yeah, so Thursday, May 14th for you all. And soon I'm going to make a quick little video just being like, hey, this is what you're going to expect for it if you do want to take it, which I would still recommend. But if you do want to take it, this is what to expect. Here's something to check to make sure all the technology is working and is in order. So I'll make that soon, and then we'll kind of have a little, hey, what do we expect? And then, yeah, Thursday and Friday, we just have reviewing circular motion stuff or rotational motion. And then, yeah, that's kind of wrapping up our review. Then next week, we'll kind of talk about like, hey, what to expect for the test. Here's some last minute free response questions if you want to try them. I'll try to be more like just on Zoom and be like, hey, if you want to ask questions, let me know. And then we'll be kind of done with content, and then we'll figure out what the rest of the year looks like. Hopefully we'll do some sort of project where you get to explore physics, but I still want to think through that a little bit more and see what to do. Yeah, and then what's due for you guys is going to just be on Wednesday, simple harmonic motion practice and a FRQ practice. But so before we talk about how Big Ben stays on time and what they need to do to keep it on time, we need to talk about how clocks work. So different clocks work differently. Of course, now you have these digital clocks that obviously don't work like this. But back in the day, when you're getting clocks and they're working, how does this happen? How does this function? How do we keep this going? So Big Ben has 3 of these gravitational pulley things, apparently, just from my quick Wikipediaing, but I don't know. But so what we have here is kind of this diagram. We have a weight that's going to fall. It's wrapped around this pulley. So that thing's going to fall, and that keeps our gear spinning. So this is an example of us taking gravitational potential energy. We store the energy in that weight, and then throughout the day, it's going to spin the pulley. It's going to turn that pulley into rotational kinetic energy. So it's going to give its energy to the rotational kinetic energy. Then over there, these parts D and F on this little like pattern diagram, we have, those are going to stop our teeth. So we'll be able to kind of like let these move like this. They're rotating along that point A over there. So if it's engaged, the gear won't be able to spin. If it's disengaged, our gear can spin. And then we have over here B and C. That's just a pendulum that's going to be spinning back and forth, and that's what's going to either engage or disengage that little stopper to let our gear spin or not, which will tick the hands of our clock. So it's really cool, and then it's somebody's job to wind up the clock, so they do work on our system. They bring that weight back up, and they do work on it and restore the energy in our system. So it's a very cool idea. It's like lots of cool things going on, and really the time that it's ticking at is defined by this pendulum over here, this pendulum that's swinging back and forth. If it's swinging, then it'll disengage and engage the gear, which will let the clock tick. And if it's doing it at the wrong time interval, if our period's not correct, then it won't keep the correct time on our clock. So we're looking at Big Ben in particular. Like I said, I think it uses 3 of those. But so it was completed in 1859. When it was completed, it was the world's most accurate, largest clock. Or one of the most accurate. I guess you can't say it was the most accurate, but it was very, very big, obviously, and it kind of keeps the time for London. I think it's in London. I don't actually know. But it keeps the time. You're chilling, and it's 1859. People don't have their phones. Maybe watches are too expensive. You know, oh, I need to be somewhere at 10 o'clock. Like, you'd have to look at this clock and be like, okay, I just heard the bells ring. I have about 15 minutes or so. This is really keeping London in order. So it's really important that it stays on time. And the reason it's important that, like, if it loses a second, maybe that doesn't sound like a big deal, but if it loses a second every day, then eventually we're off by a minute, and then you're off by an hour. So you have to make sure that time is kept. You have to make sure that the time is the time. So little facts about it, whatever, it's 315 feet tall, which is crazy. And it's really cool. So the dials of this are 23 feet. So this face is 23 feet in diameter, which is huge. Like, it doesn't look that big, but 23 feet, that's crazy. And it's famous for its reliability. And there is a clock master whose job it is to keep this accurate. So somebody is paid, somebody is employed to make sure that this clock stays accurate. And one of the main problems is, you're probably thinking, why would it lose accuracy? So temperature fluctuations actually are going to cause this clock to lose time. So we know from experiences like with when it we live in a climate where we get cold weather and hot weather. So you know that things expand or contract when it gets cold or hot. Like the road has those spacers in it because we know that roads expand. Maybe sometimes like in the winter your door is like a really like loose fit in the door socket and the door the door jamb, I don't know. And then in the summer maybe it's like harder to close because that door expanded because of the temperature. So temperature is going to cause our pendulum to either grow or shrink, and that's going to make us lose time, and that's not good. So what we want to figure out is, how could the clock master fix the period of the pendulum to keep the time correct? So we'll kind of review a little bit of simple harmonic motion, and then we'll examine this idea and come to a conclusion, come to an answer. But so yeah, let's review simple harmonic motion. So the first thing we want to talk about is this idea of equilibrium and oscillation. So to kind of guide us with simple harmonic motion, to get us back into it, let's picture a marble in a bowl. So we kind of see this cross section of a bowl, and at the bottom we have a marble. And if we put the marble at the bottom, it's going to be in what we call the equilibrium position. And that's just going to be this position where our marble is in equilibrium, which we defined earlier back when we talked about forces, a spot or a state where our object has no net force acting on it. So yeah, we have the gravitational force going downwards and the normal force pointing up, but overall there's no net force acting on this marble. If we just put it right at the bottom, it'll stay there, it won't accelerate, there's no net force acting on it. So now let's picture a situation if we push it away from equilibrium. So you've maybe done something like this before, you can envision it pretty easily. If we push the marble away from equilibrium, well, what's going to happen? Well, we know that it'll kind of go up here, and it'll move back and forth. So we know that it'll move back and forth. And if we think about why that's happening, well, now the marble has a net force acting on it. So we see, if we kind of look at this force diagram, it's a little bit small, sorry about that. We have gravitational force going down, the normal force coming out at an angle, the normal force perpendicular to the surface is going to be canceled out by the perpendicular component of gravity because it's not accelerating up off the ramp or through the bowl. And we're left with a net force, this gravitational force, that's pointing kind of down towards this equilibrium position. So the marble now, by being away from equilibrium, has a net force acting on it. And this net force, we're going to call it a kind of special type of force. So it's not like a new type, it's not like gravity or the normal force or the spring force. It's just kind of like when we had centripetal force. We said, hey, the forces that we used to know are acting in a different way now. So the centripetal force is made up of these other forces. Like every other type of force can be a centripetal force. Same thing here. We can have the forces that we're used to act as a restoring force, a force that's acting to restore equilibrium. So in this case, our gravitational force is acting to restore equilibrium. It's trying to get the marble back to that equilibrium position where it was at the bottom when it had no net force acting on it. And we see in this situation, and what we'll see in all situations, is that the magnitude of this restoring force is going to increase if we're further away from equilibrium. So if we're further away, we'll have a larger restoring force. So then if we think about what would happen, yeah, it would return, but it wouldn't just go back to the equilibrium position and stop. And we know that because objects have inertia. We studied Newton's laws, and we know that this first law is this law of inertia, that if an object has mass and it's moving, it's going to want to keep on doing what it's doing unless an outside force acts on it. So down at the very bottom, we have no outside force acting on it. Our ball was moving. It wants to keep on moving if we picture it being frictionless, right? So we say, okay, we're dealing with this balance of inertia and the restoring force. So this object at the bottom is going to want to keep on doing what it's doing, and as soon as it gets away from the bottom, it's going to have a net force that's acting as a restoring force to get it back to equilibrium. So we see this oscillatory motion where it wants to return, and then the restoring force is bringing it back, and then that inertia is carrying it, and the motion repeats itself. We have this oscillatory motion. So oscillatory motion is defined by a few things, and one of the most standout things about it is that it has this quantity that we can define as the period. So oscillatory motion has a period where the period is just defined as the time for one oscillation. Other ways to think about an oscillation is really just one full cycle, or what we called it in class when we were working with it, one there and back again. So you start at one position, you go away, and then you go back to where you were. So that full there and then back, that's one cycle, that's one period. So the time that it takes to do that is going to be a period. So our symbol for period is going to be this capital T, and it's going to be in units of seconds per cycle. So how many seconds, how much time for one cycle. Another quantity that we can define when we have oscillatory motion is the frequency. So the frequency is very similar to the period, except for instead of counting how much time it takes for one cycle, we count how many cycles are happening each second. So we're going to use the symbol lowercase f to define that, and the frequency is really just 1 over the period. So how many cycles do you have in each second? So let's say we have a period. Let's say it takes 2 seconds for one complete cycle. So it takes us 2 seconds to go there and back again. So our period would be 2 seconds for every one cycle. Our frequency would be the inverse of that. It would be 1/2. We'd say, okay, for one cycle, it took us 2 seconds. So one cycle every 2 seconds, that would be a frequency of 1/2 or 0.5 hertz. And the other thing that's going to define our oscillatory motion is that it's going to be characterized by a sinusoidal graph. So if we were going to graph this, if we were going to do a position versus time graph, we would see that this motion would follow a sine shape. And the period that we just talked about, the one thing that's really going to define us, is going to be shown by one complete sine wave. So one of those sine waves. And let's look at how this applies to the marble and the bowl example and kind of get a little bit more context. So if we were looking at this, let's say we start off at this maximum position to the right. So we start off with this maximum position. We're going to call the equilibrium position 0. So we'll say, okay, we're starting to the right of 0. So this is positive. We have this positive position, this positive displacement. So if we draw that out, we'd say, okay, here's 0. We're starting at time of 0 at a positive position. Throughout this time, if we just kind of then drop it, it'll roll backwards. This restoring force is acting on it. So it'll roll back to the equilibrium position. So we see, okay, it goes from positive to 0 position, where we're calling 0 our equilibrium. And then we said, okay, this thing has inertia, it's moving, it's going to keep on going. So then it's going to go up to our negative position to the left of 0 and reach that maximum. And then again, same thing, it'll say, okay, well now I want to restore it, the restoring force is acting on it. It'll go back to the equilibrium position, and then it'll get back, because of inertia again, to the initial position. So this right here shows us one full cycle. This is showing us one cycle of a sine wave. So this motion is one complete period, one full there and back again. So we see, okay, one cycle of our sine wave gives us one period. And this oscillatory motion, this sinusoidal motion, is what characterizes our simple harmonic motion. And then just a few features of this graph. We said the period is showing us one complete sine wave. So we saw, okay, here's one complete sine wave. So that's a period. And then the amplitude is another thing that we have to define. The amplitude is just the object's maximum displacement. So here we see the maximum position that it gets to is on these sides of the bowl. So it's kind of showing us the maximums of our graph. So the maximum, that's just the amplitude. So the amplitude would be from this positive to 0. How many meters away is the maximum position from equilibrium? That's what our amplitude is going to show us. And then if we want to go a little bit further with it and graph other features, we could graph the velocity. And we see that the velocity also follows this sinusoidal motion. It just looks a little bit different. So here's our position versus time. We see the velocity, same kind of shape, just a little bit different trends. So if we're looking at this and we have the same exact motion down here, at the very starting point where we were holding the marble up at the top, here is kind of where it's at rest. We bring it up to the top, it's not moving, so over there we have a a 0 velocity. So we have 0 velocity at the top, then we let it go, and this marble starts to roll to the left. So we said, okay, if something's moving to the left, that's going to be defined as a negative velocity. So it starts moving to the left, and it has a negative velocity. Eventually, it'll reach the bottom of the bowl, which is where we have the maximum velocity. That's where it's moving the fastest. So we have it moving the fastest down at the bottom. It's still moving to the left, so we still have a negative velocity, and it'll reach the maximum. So it's negative maximum, where again, it'll come to rest. We have this restoring force acting on it. Eventually, this restoring force has accelerated it to 0 meters per second, to a speed of 0. And we have this 0 velocity. And now it'll start rolling back, and this time it's rolling to the right. So this time it has a positive velocity because it's rolling in our positive direction. So we see it starts to build up speed until eventually it reaches the maximum down at the bottom. And then same kind of thing, it'll slow down then after it reaches the maximum until it comes to rest because the restoring force is acting on it to slow it down, to bring it back to the equilibrium position where it wants to go. And again, here we're tracing out one full cycle, so the time would just be our period. And if we want to do acceleration versus time, we could think about it in the same kind of way. So acceleration, we can think about it as how much force do we have? So where is our force the most? Where is our force the least? And what direction is it acting on? So here, when we're at our maximum position, we know that the force is going to be a restoring force that wants to get us back to equilibrium. So over here, we say, okay, well, it's to the right of equilibrium. This restoring force wants to push it back to equilibrium. So it's going to push to the left. And we said that the force is going to increase with the distance from equilibrium. So here we have this maximum restoring force, and it's pushing us to the left because it wants to go back to equilibrium, which is to the left of our position. And force equals mass times acceleration. So we can say, okay, our force is directly related to acceleration, so we're really just thinking about force. But so we have this negative acceleration. Eventually over at this equilibrium position, we said we had no net force, so we have a 0 acceleration. Over here to the left, we said, okay, we're to the left of our equilibrium position. It wants to go back to our equilibrium position, so it's going to push to the right. So we're going to have a positive acceleration. Then again, 0 at equilibrium, and then same kind of trend back where we started. Again, this full cycle, this full sine wave is going to be our period. So on our time axis, that's 1 period. And then if we think about, well, what forces can act as restoring forces? So the two forces that we're going to look at that can be restoring forces are going to be springs and are going to be gravity. So spring forces are going to show us oscillatory motion or simple harmonic motion for objects that aren't springs. Those ones are pretty nice and obvious. And then gravity is acting as the restoring force when we have pendulums, or our example of a marble in a bowl, where we have a mass that's just kind of moving back and forth, tracing out this motion. So this is our pendulum, where gravity is our restoring force, and then the spring, we have the spring force acting as our restoring force. And then one other thing to talk about really quickly is energy in our system. I should have put this before, sorry about that. But so we know that in our system, if we have no outside forces acting on it, the energy is going to be constant. And when we have this type of motion, that's either pendulum motion or spring motion, we see that our energy is being constantly converted from potential to kinetic to potential, while that energy stays constant. So we can think about this energy graph. If we were going to graph energy versus time, it would also be sinusoidal. It would have the same shape as our position versus time, velocity versus time graphs. So if we're looking at this, we can just kind of identify what points do we have maximum potential energy. So over here at the right side, when we had our maximum displacement, we were at our maximum height, which means we have our maximum gravitational potential energy. And then when we're back at equilibrium, we have 0 potential energy. We are at our lowest height. Then when we're back up here, we are at a positive height. We are at a positive potential energy, back to our maximum, 0 at equilibrium, and then back to our positive maximum. So we would draw that out for our potential energy, and then say, well, with kinetic, I know that my total energy has to be conserved. I know that my total energy has to be constant. So at every point, my kinetic plus my gravitational potential energy has to equal the total energy, and that has to equal a constant. So we would just kind of draw in the reverse for our kinetic energy. And let's see, does that make sense? We said at the top we have no velocity, so we have no kinetic energy. At the bottom, at equilibrium, we have our maximum. We said we're moving with our maximum velocity. Then we have 0 again at the top, and then we have a maximum again at the bottom at equilibrium, and then 0 again at the top. So we're saying, hey, that makes sense. We have this constant energy. And yeah, so energy can be graphed in a very similar way. The only really difference is with energy, it's going to just be a positive quantity. We're just going to deal with positive energy. So we would notice, hey, if we had this like position graph, or more so the velocity graph, when we looked at our velocity versus time graph, it went negative, right? But with velocity, or sorry, with kinetic energy, our equation is 1/2 mv squared. So we don't really have, even though we have these negative velocities, we have to square it to get kinetic energy. So it's going to be positive, and then it's going to repeat itself in half the time. So instead of going, let's see, like 0, negative, 0, positive, this is repeating itself 0, positive, 0, positive, 0. So our shape of our graph is a little bit different because it's based on v squared instead of just velocity. And then kind of last little bit, if we want to find the period of it, there's equations that we can do, but we're just going to kind of get these equations. So the period of simple harmonic motion is determined by physical properties of the oscillator. So it's based only on the thing that you have created, the oscillator that you've made. So if we're dealing with a spring that's oscillating, it's going to be based on the mass that's attached to that spring, and then the spring constant, so that'll affect our period. And then our pendulum, it's only going to be affected by the length of the arm, that L, and then G, the gravitational field on Earth, 9.8. And then another big idea, the period does not depend on the amplitude. So if we look at both these equations for period, Ts for period of a spring, and then Tp for period of a pendulum, none of these have amplitude in them. So they're only based on the actual oscillators themselves, the things that are oscillating. And then if we're thinking back to this main idea, we're looking at, okay, Big Ben is losing time. This temperature changes are causing this L to change. Now how can we do, what can we do to fix it? So I have a quick video of somebody fixing it, but I won't show you like why that's happening. But if we look at this, what this person does, this is the clock master. He takes a penny, that's what he calls it in the video. So I don't know if they call it pennies in London. And then he just puts it on the pendulum. That's it. He goes over, he says, okay, put a penny on it. That fixes it. That'll get our time back. So that's kind of weird, right? Like, how does that happen? How does putting a little penny on it, how does that change it? So what I want you to do is make a quick little prediction. Think to yourself, based on this equation, how does a penny change it? Like, we said mass doesn't matter for a pendulum, and that clearly is a pendulum. So what's happening? How does that change it? So think about that for a quick second, and then we'll get to it. But yeah, so what we talked about when we got to rotational motion is that all objects have this center of mass. So all objects have this location where you could balance them from, where you could pretend, okay, all of the mass is concentrated at that one position, and then, oh gosh, that didn't work well at all. So all objects have this little center of mass where we can say, okay, objects will balance through that center of mass. And then when we do any really physical analysis about it, we just kind of pretend that all of the object's mass is concentrated at that center of mass. So if we have this pendulum down here, we have kind of this ball at the end. We say the center of mass is right there. And the L in that equation, the length of our pendulum arm, is going to be from where our object's swinging around to the center of mass. So what's weird is if we add a little penny to there, we're actually changing the location of the center of mass. So we're kind of raising, or we're lowering that L. So we're saying, okay, now we've moved it over a little bit. Like if you picture, oops, say we're balanced right here. If we add some more mass up here, we'd have to move where we would balance it from. So we're technically, by adding the mass there, we're changing the center of mass, and we're changing the length of the pendulum arm. So then if we look at our equation, we say, okay, well, L went down, which means that our period would go down. So that would help us fix that expansion that we have from that change in temperature. Or we could take pennies off if it contracted. But yeah, so I just thought that was kind of cool that it's such like a simple fix. All we're doing is changing this length, and that'll fix our period. And that's kind of cool, especially because like we can't stretch the pendulum. Like, this is made out of metal. Like, we can't physically go in there and be like, okay, I'm going to make it smaller or bigger. So we had to come up with creative ways to change that length. So that's just kind of a cool little thing. Hopefully this is a short little review, and then I'll get you some problems. But yeah,